you may have already guessed, we're dealing with a great mind here, and it's somewhat intimidating sometimes. So, but Harold has a range of interests. Just about anything dealing with severe weather meteorology, Harold's good at, and he's had some great things, especially about probability forecasts, which I think is great. Today he's going to be talking about some new insights into tornado climatology and severe thunderstorm climatology. So please welcome Harold Brooks.
Thank you. Okay, just for well, at least one of these addresses will come back up. You can get to anything, almost anything I'm going to talk about today from my website, which just is the which is just the Tilda Brooks. And then if you want to do funky other things to go with the little specific parts, it's in Tornado, and it's also in potpourri.html, and threatandem.html, which is, I think, which is new stuff that I think is pretty exciting. I have two kids, one of whom is a 7-year-old daughter who I believe has the distinction of being the youngest chaser to get a tornado. She was 6 months old when not one. She was actually fairly helpful on the trip. I mean, she was polite, yeah, and didn't do anything while we were in the storm. But she's ADHD, and I've determined after having watched her behavior, I'm a little bit of an ADHD scientist. Paul made the comment that I have lots of interest, and what happens is I tend to sort of jump around from thing to thing and may be really active for a year or two doing one thing, and then I'll just decide I'll do something completely different for a while. Like I used to write numerical models all the time, and people still think I do, and I haven't actually initiated a COD scale model for 2.5 years. I'm going to talk about some of what I think are the fun things I've been doing for about the last year, and they deal with the climatology of severe thunderstorms. And in large part, this is driven by the fact that the group that I'm head of at NSSL, our primary task is to interact with the SPC and to do research that helps their forecasts. So this will have a very SPC-ish orientation, which means I'm not interested necessarily in the individual storm so much as, say, things that happen on a 6 to 24-hour time scale. And the questions we're going to try to look at are, what are the data like? What are the distribution of threats, and can we detect any changes in those threats and effect? And we'll go ahead and start with an effect. I also end up dealing a lot with the media, who ask interesting questions sometimes, and we try to steer them in the right direction. This is a record of tornado fatalities since 1880 in the United States. And some points to make. That's tri-state tornado, 700 fatalities. This is the annual numbers. The black curve is a smooth curve. Put a simple filter onto it. And one thing I'd like people to note is that we sort of see this somewhat of an increase, and then maybe it looks like a decrease. We haven't had any really huge years since the early 70s by looking at this. Even without tri-state, the 1920s were the deadliest decade in the U.S. You throw out the 700 fatalities with tri-state, and the 20s were still the deadliest time. There were a lot of years where a lot of people got killed. Well, let's look at. I want to try to look at how the death rate has changed and what's changed it. This is a record over that same time period of the number of killer tornadoes per year. And again, the heavy line is a smoother that we put onto it. And you see, perhaps there's been a decrease since the, say, 20s through 30s, where we used to average about 40 killer tornadoes a year. For now, it's about 15 to 20 killer tornadoes per year in the United States, on average. If we step back even one more step, I like to look at things on days. Yes or no, something happened on a day. The number of days on which killer tornadoes occur in the U.S. per year hasn't really changed very much since the 1880s. We have somewhere between 12 to maybe 20 days of tornadoes that kill people per year in the U.S. Last year we were at 20. And, this minimum right here in the early 60s looks a lot like this minimum in the 90s. And I'd be hard-pressed to say that we've done anything that actually has limited the number of days in which people are killed. We have fewer tornadoes that kill people, but we have the same number of days. One method we tried to look at was, what's happened to the really big killer events? This is what I did was I took all the killer tornadoes 5-year period and looked at what the 95th percentile of the death number in there was. So I eliminate, say, Tri-State, where 700 people were killed, but I look at the pretty big tornado killer. So maybe in a period that the 5% of the tornadoes killed more than this number of people. For instance, in the period around 1953 to 57, 5% of the tornadoes killed 40 or more people. In the period 1980 to 84, 5% of the tornadoes killed 5 people. That's what this plot is. Again, the red line is now smoother. And this starts to look like one of the things that's happened since the mid-1970s is we eliminated most of the really big killer tornadoes. A big killer tornado event now is killing 10 to 15 people. Back 40, 50 years ago, that was a number that was 25 to 30 people died in what we consider big tornado events, individual tornadoes. I can't explain all the reasons. One thing that happened in here, spotter training. We had storm intercept, started explaining a lot of what was going on, research into the radars to help us understand signatures of what was going on. And about the mid-1970s, perhaps public awareness after the April 34th outbreak, we started being able to at least limit the high-end killer tornado events. If I can go back to that original plot that I showed of the number of fatalities per year and scale it by the population of the U.S., the jaggedy line is the number of fatalities, raw number of fatalities, or the rate of tornado fatalities per year. Then the slightly smooth red line is just a little bit of filter to the data. The green lines represent long-term means, or long-term trends in that direction. This is a log plot of 10 fatalities per million, 1 per million, down to 100 per million. And these blue lines represent the 10th and 90th percentile of the fatalities over the last 75 years. If you look back at the period from 1880 to about 1925, the death rate was pretty constant. We averaged 1.8 fatalities per million people per year. Population increased, we have larger death toll during the year. Since the mid-1920s, there's been a long-term steady decrease in the rate of tornado fatalities. Where we now think of as being a big year would have been a small year years ago. If we look, say, for instance, last year, 1998, is the third highest anomaly above this long-term trend since 1925. But one way to look at this is, let's assume, and the reasons why this decline has taken place are complicated. We do better communication, perhaps better building. The increase in population in urban areas may be a help, plus what we do in forecast and warnings. All those things contribute to this decline. If that decline hadn't occurred, and last year would have been just as far above the long-term mean as what it was, we would have had 1,800 fatalities in the U.S. last year. As it was, there were 129, which is now a huge number. But whatever results in the system, one naive estimate of the how many lives we saved is that we saved about 1,700 lives last year. From everything that goes on in the system and things that go on outside of the system. Okay. You're going to see about 3 or 4 short talks in this presentation. I'm going to summarize what we know about deaths. Killer tornadoes, the number of killer tornadoes have dropped down. The big death toll has dropped down, but we haven't changed the number of days in which people get killed. We still have several days a year where 1 or 2 people get killed. And that may be very hard to get down any lower. We've had long-term decline since 25, and 1998 is the third biggest anomaly since then. So it was a big year, but some of the media reports were making it sound like it was, beyond anything we can imagine. I'm going to look at 2 data sets for most of the rest of the time. And we're going to spend a little bit of time looking about the changes in severe weather reports through time, and then try to make some estimates of what climate ecology really is. We're going to use the SPC log, that's in storm data. That's the official record since 1950. There's a big change in 1954 when the Severe Storms Project had its first full year. So I'm only going to use the data since 54. And severe weather, tornadoes, thunderstorm winds greater than 50 knots, and hail 3/4 inch. And I know the location and the time of all of those reports. And then the Grisula significant tornado data set from 1680 to 1995. And for that I have it listed by county and the time of the F scale of the event And all I'm going to use today is the daily and stake data. There are 13,486 entries in the Grazoulis book. And I'm going to primarily, as I'll show you in a few minutes, focus on the period since 1921. And from 1921 to 1995, there are about 10,000 entries in the Grazoulis data set. And Tom was kind enough to provide that for us. Some things we'd like to be able to do with looking at severe weather changes through time. We'd like to be able to monitor any changes in forecast performance. Are we actually getting better at forecasting them or not? And ideally, we'd also like to detect potentially significant changes in climate changes. One of the tenets from the climate change community, which I did my master's work in, is that changes in the climate may lead to changes in extreme events. Severe thunderstorms are a likely place to look for changes in extreme events, and we're going to try to see if he would say anything about that. Since 1954, this is the record of tornado reports in the United States. The red line is the raw number, and it fits a fairly nice, not too badly, a linear trend, increasing about 12 reports per year. If we assume that now is truth, we're getting this that we used to really underreport, and I think the evidence is fairly strong that this isn't a change in the actual record. If this is the real, if this is just a function of better reporting, then, and we assume that these fluctuations off of this long-term trend are real, this blue line represents an estimate of what we would actually have observed if we had today's conditions going on back in the early 50s. And for the old-timers, like Les, one of the things that's highlighted, the two big years of all time, 1957, which Les remembers at least one tornado from, and 1973, probably the two biggest tornado years in the observation since the cell log started. 1998 comes out as the third or fourth biggest year, I think the fourth biggest year on the record, based on this kind of a measure. If we look now also, instead of just tornadoes, let's look at the number of tornado reports and the number of non-tornadic severe weather reports. The red is the number of tornado reports multiplied by 10. That's what I showed you just a minute ago. And a nice slow increase. The number of non-tornadic severe weather reports, do this, growing from around 2,000 per year up until the mid-1960s. Where now, last year, we had just under 20,000 non-tornadic severe weather reports in the log. The two data sets don't look very much alike. I can deal statistically with a linear increase. This is a little bit harder to do anything with. And if we say, okay, well maybe we're just reporting more events on a particular day, maybe we can do something else by just looking at how many days per year do we report severe weather. The red is the tornado again, blue is non-tornadic. The trend in the tornado reports, days with tornado reports, is a slight increase from maybe 155 up to about 180. But then there were big years in the early 70s. The late 80s were really awful. And there's a slow increase. This works out, if you fit a linear fit to it, it's half a day per year. The non-tornadic reports have gone from around somewhere in the 180 to 190 range up to 260 to 270 days per year. Been going up by 2 days per year. We have 2 days more each year that we report severe weather than we used to. To where around, I think it's around 2025, if this trend continues, we will report non-tornadic severe weather every day of the year. Well, it doesn't mean it'll be there, we should report it. Or maybe it's there already. I want to look at some of the actual, I'm going to focus for a minute on the non-tornadic severe weather. This is the distribution of hail reports by hail size. In two periods, 1976 to 1979 and then 1995. The red is the 1995, the blue is 76 to 79. You'll see immediately there, and then the size, the diameter, in hundredths of an inches down here along the bottom. And we sort of clump reports into some groups. Something around 3/4 of an inch. Maybe the one report you can put somewhere, but then something around golf ball size, baseball size, bigger. And in each one of these periods, From 76 to 79, and again from 90, and again in 95, there's one lone report of 1 1/8 inch hail. Now, I want to find this spotter who goes out on his own with calipers, I suppose. So when I see this, I can't make heads or tails of that kind of data. So what I did was I grouped the reports by size, and this isn't anything new. People have done this before. But I basically say there are about 4 categories of hail that we report. We report small change, we report golf balls, we report baseballs, and we report really big stuff. And this is on a log scale. The reports from 1995 are in the red, and 76 to 79 are in the blue. And from assuming that this is what a statistician would call a rare event, you expect this to decline logarithmically as you go up in scale. So these lines should theoretically be straight lines as we go along. And in 1995, it's pretty close. Looks like in the late 70s, we weren't reporting the true frequency of the small hail. If this really is a straight line, and from the golf ball size scale on up, it is straight, we're missing about 18,000 reports from the late 1970s of 3/4 and 1 inch hail. When Don talked yesterday about raising the size of the hail criteria, one of the things that happens is that, to me, what I would do is say, golf ball and higher, we might be able to, we could make a big change. Trying to cut off and say 1 inch or something, I don't think we'd have much of a change. We'd have much of a change, and most people would end up calling what they call now 3/4 inch hail. They'd make it into 1 inch hail. And there's perhaps a slight hint that we're getting a little bit of the reports are getting a little bit larger. The slopes of these lines are a little bit different. We seem to be reporting softball and grapefruit size hail just a little bit more often now. We can do the same thing for wind gusts. This is the data from 1986 to 1995, and the blue is 96 to 97. And again, we see a slight increase in the log scale, about the same number of reports in this 10-year period that there was in this 2-year period. We report a lot more. And the slope is this linear fit to that. We perhaps are a little more likely to report larger hail, or larger wind gusts. Just slightly. The biggest change that's happened in the wind report database. This is the percentage of total wind reports that are listed in the cells log as being in the blue without a wind gust estimate on it. That they're listed as either unknown or just a dollar damage amount set on them. And the red is the number of reports that are exactly 50 knots. In 1996, there was a change made in the way that the data are recorded, and we dropped from having about 75 to 80% of the reports not having a wind amount associated with them down to only 45% of them, and that entire increase basically went into 50-knot wind reports. From the mid-70s on to the mid-90s, it was about 5% of all wind reports were listed as 50 knots. From 1976 on, that number is about 20%. If you use the database for attempting to do any climatologies, the change in the way that things are reported in 96 and 97 has made interpreting the wind data very difficult at the low end. So 50-knot wind gusts don't mean very much. And we can start to see what's happened to the number of reports per day, non-frenetic. This is just looking at the number of reports on a given day through time. Log scale again. Almost everything we do with non-frenetic reports has to be done on a log scale because of the large changes. Back in the mid-50s, there was 1/4 of the days on which severe weather was reported had 3 or 4 reports of severe weather. 75% of all of the days that severe weather was reported had 3 or less non-frenetic reports. Now, 3/4 of the days now have 50 reports or less. What we think of as a big day is radically different. And if you want to go back to do case studies and say, I want to look at big days. If you put some threshold that says, like, well, 20 severe weather reports on it, you're going to be collecting things that are now at about the 50th percentile. Whereas in the early 70s, you're looking at something that was the extreme event of the entire year. So the changes in reports have changed what we think is going on out there. To summarize this part, we've had a large increase in the number of non-tornadic severe weather days, not much in tornadic days, and I'll show you in a minute that there's a little increase in the number of significant tornado days. We've had an order of magnitude increase in what we think of as a big day. There's some implications of this. The tornadic reports are up by about a factor of 2 in the last 40 years. Non-tornadics are up by 20. And we have actually looked at the distributions. Most of the tornado increases in the low F scale, and the hail is in low size severe, particularly starting somewhere in the late 80s, early 90s. And the big change in the record is 1996, when they changed the way that it's recorded. And we may have had some inflation of the severity of reports, but not very big. I do a lot of work on verification. And these reports have a huge impact on on verification. If we don't do anything to try to correct for them, it improves the scores at the SBC, the national level scores. In fact, the change in the number of reports is the dominant term in any of the simple measures that have been used in the past to describe the forecast performance. All other things being equal, it ought to improve the local office scores. There really hasn't been as much of a change. From my pure verification standpoint, having the local warning offices collecting observations to verify their own warnings is just, it makes the believing any local office numbers that describe local warning performance almost useless. Because when that puts that means that a forecast might affect what they actually do to come up with what they call the observation. We may be closer to what the truth is now. We may know what's going on out there the last few years better than we ever have known it before. I believe that probably the historical record of verification of severe weather warnings has little or no meaning. I don't think we can say anything about any trends that says very much without doing some more sophisticated work on it, which we're only just getting started. And due to those changes in the reports, we will be able to determine if there's a change in severe weather frequency, perhaps say associated with climate change, even if the signal is very large. We've got an order of magnitude increase in the number of reports over the last 40 years, which I think is probably associated with just the changes in reporting method. Could be related to something else, but that as a result we have no baseline that will allow us to say very much, which is a little, basically just looking at the raw data. And that's a perhaps disturbing thought. I'm providing input for the Intergovernmental Panel on Climate Change on this issue. I don't think they're going to be real happy here, exactly what I said. I'm going to switch gears. We're at the third talk. These are all conference talks we're going to include. We're going to define this. I'm going to now look at just the climatology of a variable which actually may be able to tell us something. We may be able to see something in this variable when things happen. Significant tornado day. That's defined as a day with one or more F2 or greater tornadoes within a certain location. For the most part, I'm going to look at the United States. And I'm going to use Tom Perzula's database for this, because it's longer than the self-log. And we're going to do some tests in the next few months that'll show, so I think it'll probably show that it has statistical properties like the self-log. There's been no long-term increase since 1921 in this variable. The mean value 53 days per year with an F2 or greater tornado, and the total range has been 33 to 80. This is a plot of the number of days per year with a significant tornado somewhere in the U.S. since 21. And again, I put a smoother on here. Boy, the 50s through the early 70s were big. There was an increase early on, but we've seen now that I'm not convinced that there really weren't a whole lot more big tornadoes back in the 50s, or days with big tornadoes back in the 50s through the 70s. 1950, I think that's 1949 actually, is the day with, I think it's 49 the year with 80 days of significant tornado. The fewest is 1987 with 33. And anybody who was in the plains in the late 80s remembers that quite well. If I look now, I want to look at what the annual cycle looks like of significant tornadoes. And this is a plot that shows the raw count out of those 75 years, what percentage of the days had a significant tornado. So that for, I think this is like May the 23rd or something, 47% of the 75 years had a significant tornado on May the 23rd. This is the annual cycle. Raw data. It goes up. April and May are pretty good. Down here, maybe there's something going on here in the fall. What I'm going to do is smooth this data. And I think this is the only equation we'll see. Using a Gaussian smoother, bell curve. I'm going to smooth the data out. I'm going to assume that what I'm basically assuming is that the fact that a tornado occurred on April the 16th tells me something about the probability of one occurring on April the 17th. Doesn't tell me a whole lot about the probability of one occurring on May the 16th, but I'm going to sort of say I'm looking at things kind of with fuzzy glasses. And this is a smoother. The effect it has on the data is I take information from a point, and as I make the smoother, and make it a larger, this is the values of the smoothing parameter, it essentially spreads information out over a lot more days. If I looked at only one day, if I didn't have the smoother, this value would be 1 at the axis, and as it is when I'm doing the smoothing it out more and more and more. And I want to show you the effect of that on what the annual cycle looks like when I apply that smoothing. If you get into objective analysis, this is essentially what I'm doing is objective analysis, because I don't care what the exact values of the points are. I just say that everything's 1 or 0. If I put on a smoother that has a fairly light smoother that doesn't do much, I get the blue line. And now you can start to see the annual cycle a little more clearly. As it goes up, the peaks fall down quite a bit, and you see some fluctuations in it. And here's sort of the general trend. The spring is more likely to have significant tornadoes than the fall. If I put on a heavier smoother, I get the red line. And this starts to look like, this is a fairly smooth thing. We have a little bit of a bump in the fall, pronounced maximum in the middle, and in the spring we're about 30% probability of having a significant tornado any day. And what this is trying to do, if a statistician told you, what I'm basically assuming is that somewhere there's this underlying statistical process, and for 75 years we've been taking random samples from it. And now what I'm doing is trying to pull back out what that underlying distribution is, and I can use this now to do lots of powerful things and work on the smooth data rather than on the raw data. And what this allows me to do is that I can't see the small scale fluctuations anymore, but the things I do see are strong signals. All I see are the strong signals when I do this. This is what I get if I do that over the individual periods of individual 15-year periods, to give you some idea of the variability over time. The 15-year period from 1951 to 65 is the biggest threat time of the entire record. So that when people like Les getting excited about the Ruston Heights tornado in 57, that was a good time to be looking around. If you look now at the early years, the 21 through 35 is this red line. The 1981 to 95, the most recent 15 years, is the black line. And those two records are roughly similar. There's no real indication that we've had any long-term secular increases in this variable. It may really be true that the 50s from 51 to 80 roughly were big times. So we got started too late. We can also look at, I can do some things, I can actually look at this by each state. And I can plot when the maximum occurs in the record for each state during the year. The yellow points are in the spring, oranges are in March and early April, yellows are in May, late April and May, the greens become late May, early June, and the blues become sometime in the summer. progression of the tornado threat through the year, from the southeast through the central part of the U.S. and then up through the northern plains. And then things on the Oregon and Washington, you know, it happens whenever it wants to, I guess. There's no real annual cycle that occurs out there, and the threat isn't very big, so who really cares? No, self Russia, there you go. I can also make estimates now using that of what years were the most alike. You know, people, you know, every once in a while I see in discussion groups and all things like, well, you know, this year is going to be a lot like 1980, you know, pick a number, or this year reminds me of 1973, you know, or whatever. Well, we can now make unbiased estimates of the most alike years. And these are the 3 years in that 75-year record that were the most alike in terms of when tornadoes occurred. 1936, 1993, and 1994. Those years look kind of alike. One thing we want to try to do at NSSL over the next decade is to go back and do synoptic climatologies that go with us to try to identify, well, is there anything we can see in the synoptic scale features that will tell us, well, in the long term over this year, that really show what they were alike, with the idea, who knows, about the day after I retire, that we can start trying to do seasonal forecasts of severe weather threat, sort of like what Bill Gray tries to do for the hurricanes. Years that are unalike, these are the most different years in the entire record, 1921 and 1992. In 1992, not a whole lot happened in the spring. 1921, man, you know, that must have been really huge. I mean, things were happening all the time in early 1921, and then the season shut down. This actually looks, I don't have the data for last year this morning, this looks a lot like last year. Where big early spring, and then once we got to the middle of summer, it's over. Whereas 92, we had a great summer, but a lousy spring. This is looking on a national scale. I'm only going to ask once. What's my time to end? I didn't see one.
We got at least,
what?
At least 40.
Oh, at least 40. Okay. We can build. Well, I'm going to do something daring. I'm going to use a statistical technique. I'm going to describe a method that we've used to try to generate fake data, to try to look and see what's significant. Were the differences between 1921 and 1992 actually significant? Or was it the kind of thing you could happen just by random chance? And we're going to use a technique called the Markov Chain, originally developed by a man named Markov. And it estimates the statistical properties of the data set, and it takes advantage of persistence. The fact that a tornado occurred, if you look at the records, the fact that significant tornadoes occurred yesterday means that it's more likely that one will occur today than the significant tornadoes hadn't occurred yesterday. And it's based, the technical details is based on what we call transition probabilities, that essentially today depends only upon what happened yesterday. And it knows, and sometimes it knows about synoptic scale systems because of that day-to-day coherence, but it doesn't know about seasonal patterns. And what they look like, the probability of having a tornado, given that one occurred yesterday, is the red line. And as it goes through the year, if you have a tornado in late May, significant tornado somewhere in the U.S., there's about a 45% probability that you'll have one the next day somewhere in the U.S. In the middle of winter, that drops down to about 18%. If we don't have one today, the probability of having one tomorrow is given by the blue line. And this is based off of the long-term, the 75-year record. And in the middle of May, it's about 22%. And in the winter, if you don't have one, there's only about a 5% chance you're going to have one the next day. One of the big things this lets us do is to start generating lots of data. And in fact, what I did to do this was generated a 10 million year data set. And looked at a couple of things. One is significant tornado days per year, and the other is how long runs, consecutive days with a significant tornado. In the 75-year record, the longest run in the United States is 9 days in a row with significant tornado occurring. Happened twice. Never anything longer than that in the entire record. And what I can actually do with this chain is I can actually pull out an individual 75-year period. And you see, if I showed it to you, it has the same kind of variability as these observations have. You have days next to each other where there's lots of tornadoes and other ones where there aren't. One of the things we can find out, we can make estimates of, are what's the probability of having a certain number of significant tornado days per year. The raw data is this blue jagged line. There's 9.5%, which is what, 7 of the 75 years, there were exactly 50 days. Well, there were only 2 days that had, or 1 day, had 51 days. Anyway, that's, the difference between the 50 and 51 days is just statistical noise. The Markov chain in the red allows us to sort of smooth that noise out and lets us estimate that that we should see 33 years with a tornado, or 30 days with only 30 days with significant tornadoes in a year, about once in 1,000 years. We should see 85 days about once in 1,000 years. If we start having, say in the next decade, 5 or 6 years, where we see 85 days of significant tornadoes in the United States, either the way we report significant tornadoes has changed dramatically, that it hasn't changed over the last 75 years, or something's different about the atmosphere. We can now make estimates of how rare events like that are. We can also estimate the probability of having really long runs. The observed record of really long runs is in the blue line, and the Markov chain estimate is in the red line. We estimate from the chain that we should see one run of 9 days about once every 100 years. We've seen 2 over the course of the record, and 2 is not very different than 1. If we look out, we can also estimate from the chain then, in fact we have this 10 million year record, we can make longer estimates. And it turns out the probability of having a run of 13 days in a row with a significant tornado is about once in 1,000 years. Again, if we start seeing lots of runs of 13 days or more in the record, this is an incredibly rare event. And again, our reporting methods have changed, or the atmosphere has changed. That's actually probably the only way we're going to be able to detect. Statistics like that are the only thing we're going to be able to detect in the record of things changing. Now to get on to the most recent thing I've been up to, and this is what else. Oh, there's one more thing I got to stop at. Okay, after today, we're going to once again hear about how La Nina causes tornado outbreaks. Okay. From the Grisoulis data set, what I've done is I plotted up the distribution of one of the popular indices to define El Nino. It's based off the sea surface temperature in the eastern Pacific. And I plotted up the mean of it in January through April, because I just read a press release about how La Nina conditions in late winter and spring lead to big tornado outbreaks in the spring. And they specifically said March and April. And what the plot is, the dashed line is this is the probability distribution of this variable over that 75-year record. This is pretty close to being a normal distribution, centered around 0 for that winter period. The probability, I took then the 57 biggest outbreaks, 10 or more significant tornadoes on a day, somewhere in the U.S., in March and April for that time period, and plotted that distribution in the solid line. And lo and behold, it's just about a normal distribution. If there was a La Nina effect, you would expect to see a whole bunch of the solid line over here. If there was an El Nino effect, a whole bunch of it over here. As it is, these two distributions are statistically indistinguishable. That doesn't say that La Nina doesn't have an effect. What it says is that on the national scale, we can't detect it. And the problem is if you go to the regional scale, the sample size has become so small that nothing has statistical significance to it. So that and in fact, the whole reason why people assert La Nina has something to do with tornado outbreaks is April 3rd, 4th, 1974. It was a La Nina year, and to a lesser extent, 65 was a weaker La Nina year, and we had a significant outbreak each one of those years. But if you look at all the years that had La Nina, that had indices bigger or approximately the same as that, very few of the other ones had significant outbreaks. For the SPC, and if you look at their new experimental probability forecast that they're putting out for threat, we've been trying to estimate the probability of having a severe weather event, trying to come up with a background climatology so they can use it in helping formulate their forecast and identify what's a big threat. It comes out of two things. One is the new verification system, the scheme that we're starting to implement at the SPC. We'll look particularly at outlook verification, so I'm looking at 24-hour periods, and also helping the probabilistic forecasting. And what I've done to look at this, because of the side of the outlook verification, we started by looking at the SPC log for 15 years, 1980 to 94, which happened to be the time period that we could easily get all of the outlooks for that time period on the same on the same grid. That's why we focus on that period. And keep in mind the numbers of changes of reports through time. We don't want to go back too far, or the data set becomes difficult to deal with that order of magnitude change. And what we've defined is that we've gridded these reports onto an 80-kilometer grid, which is approximately equivalent to within 25 miles of a point. It's actually 27 miles of a point. Close enough for government work. And we've defined a hit, or a thing, as one or more events at that grid point in the 24-hour period. Be it a tornado, one or more tornadoes, one or more hail events, one or more wind events. If we report 20 hail reports at the same grid point, all I'm going to do is write down 1. If we report 0, I write down 0. And what we're going to do is separate that into 5-year periods, and then look at the whole 15 years as well. And I do my same. I showed you the 1D Gaussian smoother for the time thing, for the time. For the temporal evolution of the significant community, it's the same thing in time for this data set. We also do a 2D Gaussian smoother in space that has a standard deviation of 120 kilometers, or 1.5 grid points in space. So I smooth things in time and space. Again, I won't be able to see real tiny details. If you try to tell me there's a difference in severe weather between here and Rockford, what I'm doing, I'm completely wiping that out. But I can tell you the difference between here and Bismarck, North Dakota. And the method allows us to get an estimate of the mean number of hits per day at each grid point, which turns out to be equal to the probability. And the integral of that quantity gives us the number of days per year with the event occurring. The output is on this website, and we've moved some stuff up here that we're going to look at in a minute to download a little quicker. And we're going to look at, I've got several things. The total threat of severe weather during the year at every point in the U.S., and then the annual cycle through the year. And what I'll show you is some animations for the entire country. You can watch the season change. We got this up with monthly probabilities, and then I also have the annual cycle at selected points on a map. And hopefully, within about 3 months, you'll be able to look at the annual cycle for any period of the record for any point in the country, tornado, wind, and hail. And we're going to also, let's see. I guess we ought to try to go over to the fancy machines. And Morris told me I needed to practice the mouse, and I tried, and we'll just see what happens. This is, I have to point at the right thing. Morris, you were right. This is challenging. Okay, this is the total number. This is the total threat of a tornado within 25 miles of any point from this record. A number of days per year that you expect to have a tornado within 25 miles of anywhere in the country. Oranges, reds, and purples are 1 or more days. The peak value is in northeastern Colorado, almost 2 days per year over the 15-year record. You see a fairly large area with 1/4 of a day per year over the record, and the Central California Valley is just slightly below that value. I won't pretend. I'm not going to pretend to explain all the features on this. There's this lovely minimum here around the Boot Heel of Missouri. This could be real. Could be small sample size, bad reporting. There's a minimum associated with southwestern Kansas, and Jim Johnson, I want you to take care of this for us. That again may be relatively low population density. We see the two maximum in Lubbock. Oh, there is a laser pointer?
There's a laser on it.
Oh, man. Oh, that one? Man, this is, these high-tech people. It does work better. This minimum here, I don't know if it's real or not. But I don't know where many of the beaches are. But we have pretty high confidence that this area is the highest threat in the U.S. Okay, not a huge surprise. We're going to look at some details. And one of the goals of this exercise is going to be to try to make an objective definition of what Tornado Alley is. Okay, the threat of severe thunderstorm winds. Remember that the peak value for tornadoes. Okay, move away. Thank you. This is the peak number of tornado days, or severe thunderstorm days in the U.S. And a broad area east of the United States has significant threat. The red values are 5 or 6 days per year. There appear to be two swaths. There's a southern swath, and then one through the Ohio Valley that may well be associated with what Bob Johns has talked about with the derecho axis, with derechos in northwest Florida. But a large area has 3 or more days per year. Essentially everything east of the Oklahoma-Texas border has 3 days per year. Reports of severe thunderstorm winds within 25 miles of home. Contrast that to hail. And hail is much more confined. This is any 3/4 inch or lower hail report. And essentially, once you get to the western, sort of halfway through Missouri, there's a very sharp fall off. We think of Oklahoma as supposedly Tornado Alley. This indicates perhaps Oklahoma's in Hail Alley. That's a peak value of 7 days per year that I should expect to have severe hail within 25 miles of my house. Up here where you live, maybe 1 to 2 days per year with severe hail reporting. And again, it falls off very rapidly off to the east. But we can do some more interesting things with this. And we can look at the annual cycles of severe weather. I'm going to look right now at tornadoes at selected points in the U.S. And I've got all these lovely points. We'll start with, for my benefit, in Norman. And what the cycle looks like during the season. And I've broken this down. The red line is based only on the 5 years from 1980 to 84. The green's from 85 to 89. Blue is 90 to 94. And the black line is over the entire 15-year period. The peak threat, the magnitude of the peak threat varies quite a bit over that time period. The early 1980s were high tornado frequency in central Oklahoma, and the late 80s were very low. But the timing of the peak, I want you to pay attention to that, is very consistent. Within about a week or two, you can count on that in late May, that's our time of our biggest threat in Norman. But if we look a little further west and look at Lubbock, Lubbock is even more consistent in its timing. And actually, over the period of the record, the probabilities are fairly consistent peak probabilities. Now note that the peak probability in here is only 2.5%. On May the 22nd or whatever, you can expect to have about 2 to 2.5% of a chance of having a tornado within 25 miles of you somewhere in Lubbock, if you live in Lubbock. No fall peak at all, really. There's maybe a hint in early October, but really not much of a peak. But very consistent from year to year. In contrast, we can Take me back. Oh, you're a good man. And I'll let you look at Chicago. In contrast, around here, what we see is a lower probability, a lower peak probability, a slightly lower total threat, but a lower peak probability, but it's spread out much more. There's a lot more variability between the periods. In Lubbock, you can count on when tornadoes are. And you can count on when they aren't. Around here, you sort of run, it's like having a low-grade fever. You know, it kind of bothers you all the time, but you're not really, really sick. In Lubbock, you know, for about a 2-week period in Lubbock, you run about 103. Okay, let's go back and I'll show you one more. If you think this shows variability, hit the point in southeastern Mississippi, down below the edge of the map. That one. Essentially, you can count on the fact that sometime in the fall, you're going to have a threat. But in the middle of, late summer, if you get a hurricane, you got a problem. And in the spring, it could be anything. Down there's no confidence that anyone can have on when tornadoes will occur. They sort of have this really low, and there are roughly the same number of total days per year on average that have tornadoes close to Hattiesburg as there are here. But it's spread out over an incredibly broad range. And we're going to talk about the implications of that at the end. Go ahead and take that. Go back. And go back twice. You can click on any point. Let's come on down. Yeah. Okay, we're going to look, when we talk about the changes in reports, let's look at the tornado reports. This is a map which is the ratio of the early 90s to the early 80s for the number of reports around the country. Yellow indicates that there were more reports in the early 80s, or the same number of reports or more in the early 80s than there are in the early 90s. Red indicates that there are more in the 90s, so that this represents 1.5 means there are 50% more reports. 1.5 times as many reports in the early 90s in here as there were in the early 80s. This whole broad region is roughly the same number of reports in the early 90s as in the early 80s, and then maybe 50% higher up in this area. That could be changes in real weather. Out in the west, where we start to get 3 times as many reports in the early 90s and the early 80s, that's probably due to changes in reporting efficiency. Okay, this is going to work better if you do this. If we go down and look at the thunderstorm winds, we get a really different picture. Same contouring. There's a small area up here in the northern plains where we have basically the same number of reports. Everywhere else in the country is 50% more or 2 times as many reports in the early 1990s as in the early 80s. If you're trying to see what the real threat is, this presents a problem as to how much of this is real and how much of this is just a report. Okay, and if we look at hail, we see a picture that looks actually even more of an increase in reports. Everywhere south of this contour, outside of this contour, is at least 50% more hail reports now than we had in the early 80s. That's actually the early 90s. They did this for the last 5-year period. It actually even be more. And most of the country it has twice as many hail reports as they did in the early 80s. Again, it's almost certainly all due to changes in the reporting efficiency, but what your definition of what's out there is speculative. Okay, back. Okay, the heart of what this effort is to provide animations and to provide weekly updates or whatever frequency they will look at, updates of what the frequency of events are. So what this plot is, go ahead and go to the 1994. This is an annual cycle of the probability of having a tornado within 25 miles of you. The scale is the probability in the right. 1% is orange, and orange is 1% larger. The purples and the blues. The date is the last 4 numbers before the slash. So that's March 25th, April, May. And we'll go through it a couple more times. The cyan is at least 0.25% threat. We're now into September, October, and we'll watch the annual cycle as it begins. You'll see at the beginning of the year, right along the Gulf Coast. By March, it spreads into the Central Plains. rapidly moves northward through June, disappears down in the southern part. You get this large area of low threat in the late summer, and then it just disappears everywhere, and we come down into the Gulf Coast. There is the fall peak in southern Mississippi that occurs in November. We'll go this one more time, and you can watch now the fall. So there's the hurricane peaks. Now here comes the fall peak, and the second season. Okay, stop this and go back. I want to contrast that to 1985 to 89. Just to give you some idea of the variability. Starts at about the same place. Starts down in the southeast. We come up in April, and then in May, particularly actually in eastern Oklahoma and southern Kansas, there was absolutely nothing in late May or late April through May. The peak time of the year, but climatologically, if you look at the long records, February now. Actually, look at this area, and there's a large area where we never get above 0.5% probability. In the other record, the 1994 record, this area here peaks at about 2% probability at the same time as they're getting nothing in the late 1980s. So the variability is pretty high in terms of the total threat. But Lubbock is always good, and northeastern Colorado is always good for tornadoes. Okay, let's go back. Now let's look at the annual cycle of winds. Now the threats are in percent. The purple is 5% and higher. When we get to that. Early June, you get this huge area. In June and July, of high probability, 4 to 5% on any given day, having a thunderstorm, severe thunderstorm wind within 25 miles of you. May, and it just spreads over the entire eastern half of the country. That orange color there was at least 4% of a chance on any given day of having a severe thunderstorm wind gust near you. Okay, let's go back to hail. Hail looks a little different. We don't really have the extreme southeast. Hail sort of just grows in place in Oklahoma and then kind of migrates westward with a 5 to 6% peak probability. And then in the middle of summer, it dies off. So we basically, if you look over here, you never see anything more than, I think, 2% anywhere east of the Mississippi River on any particular day. Now we're into late May, June, we do get across 2%. But that's the highest end probability that we have in the eastern half of the U.S. Reaching 30%. Okay, if you want to go back. And we'll have, hopefully we'll have all of these things available where you can see the maps, the animations are available on the website right now. But hopefully be able to let you point any location you want real soon. The date of the maximum probability of having a wind during the season, anywhere in the country, we have a tornado, your maximum tornado threat. These colors, I couldn't get Jim back to behave very nicely, so the labels are a little ugly. These are by the 15th and the last day of the month. Purple is late March. The blue and cyan are, the cyan and green are April. Yellow and orange are May. The red and brown are June. July is purple and the light blue again. And then early August is green. And then this is a 2-week period at the end of November, which is when the maximum occurs in a small area of southern Mississippi. Their maximum threat from a tornado is actually in late November on the annual cycle. But you can see, other than that feature, what you see is what you would expect to see. We start with our threat down in say March, perhaps early April, and it slowly spreads westward and northward. And you sort of watch the maximum threat move from down in late May, down around Lubbock, where you're in early June, when you get up into northeastern Colorado, and then late June as you go into the further northern plains. And this is the annual cycle of maximum threat. If we go back and look at what this looks like for the other variables, yeah, we'll do that. Okay. Let's look at wind. Most of the country, according to the record, or the law, maybe not the record, about 2/3 of the area east of the Rockies has its maximum threat of severe thunderstorm winds in a 4-week period, beginning in late June, and in the purple area is a 2-week period at the beginning of July. If you get north of Oklahoma City, and east of say Jackson, your peak time of your threat for severe thunderstorm winds is at the end of June and beginning of July, over the entire country. It's a huge area where that takes place. And again, this is very different now from the tornado, and it'll be very different from the hail, and we'll look at the hail. The hail threat does sort of like what the tornado threat does. We start off in March, and it marches westward and northward in July. The wind threat, the hail threat, and the tornado threat look a lot alike for when they peak. That may be related to the fact that supercells frequently produce hail. We'll note that there's no fall maximum down in the southeast, or the fall maximum is smaller in Mississippi than the spring maximum is for hail. Whereas this contrasts sharply with what we see for the wind threat. We get severe winds out of a much greater variety of thunderstorms than we do tornadoes or hail. Okay, going back. We can also look at how variable is the peak date for tornadoes. And the colors, I've highlighted the contours here are the mean number of days with a threat. 3/4 of a day per year with a threat, and 1 day per year of threat. And the colors are the standard deviation of the date of the maximum peak threat for each one for the years, for the 15 years of the record. And what I've only shown it up to 30 days. If you go more than that, essentially what you're saying is that there's a chance that it could happen somewhere within about a 120-day period. So that there's not a lot of meaning to that. The peak in Lubbock, in the Texas Panhandle, the standard deviation gets down to about 5 days. That means you have a 95% chance of knowing when that peak is within less than a 3-week period. You know exactly when the tornadoes are going to be most common in Lubbock. You come up around here, and that peak value, that variability now is about 25 days. You can have 95% confidence of when your peak tornado threat is going to be within about 90 days. In other words, it could happen over a quarter of the year. Lubbock, we know that the threat's just there in late May, early June for the most part. Okay, if we go back, what this is going to allow us to do is to make an objective definition of tornadoality that is based on 2 simple ideas. One is you have to have a threat. I don't care what the threat of tornadoes is in upstate Washington. They don't have enough to count. So you have to have a significant threat of tornado. With this, I've defined that as being at least 3/4 of a day per year. And you also, one thing I think of is that that threat has to be repeatable. You have to know when it's going to happen. Consistency from year to year. And this contour is the area where there's at least 3/4 of a day per year with a tornado within 25 miles, and the variability of the timing during the year is less than 20 days. This is a little less for some of the previous definitions in, and it's a fairly strict definition. One of the implications of this is, let me see if I can you cover that for a second? There are, some of the things that happen in Tornado Alley as a result, we probably do a better job of forecasting there than any place else. Because we have a handle on what's, we've got some confidence. There's probably better spotting. There's also better visibility out there, which helps in the spotting. It helps increase and focus the public attention for a short period of time. Living in Norman, I know when my threat is. I know that in late July, early August, I don't have much of a threat of a tornado. In January, I don't have much of one. If we plotted up all of the major killer tornadoes, say 10 or more fatalities of the last 20 years, only one of them is inside of that area. Actually, if we wait till tomorrow, it'll be the last 20 years. If we pass Wichita Falls. Since Wichita Falls, there's only one event inside of what we define as Tornado Alley. Big killer tornado events happen outside of that area. And there are lots of reasons. One, like the forecasting and spotting, and it's not easy to get the public's attention when you've got a low-grade threat the whole time. If you live in Lubbock, you know that for that short period of time, you have to be really paying attention to the weather. It's hard to surprise people in Tornado Alley if there's a tornado coming. It's pretty easy to surprise people in Cincinnati at 5:30 in the morning if there's a tornado coming. And that just doesn't happen very often. So they aren't aware. So I think that one of the things that happens is that we just don't have very many big killer events inside of Tornado Alley. An event like late August in Chicago, nobody's thinking tornado. Okay, we could go back to them. So I think I think that's one of the things that Tornado Alley allows us to do. Oh, I shouldn't have done that. I'm sorry, I lied to you. I lied. Let's get that back. We'll get that in a second. Okay. One of the things that this also has allowed us to do is to make estimates, that this climatology has allowed us to do, is to make estimates of how rare tornado outbreaks are. What's the rarest outbreak that's ever happened? And to do that, what I've done is I can do the sync smoothing on each individual day to get a probability of the tornado occurrence on a day at grid point, which is essentially what you'll see from the on the SPC forecast. And then we compare that daily probability to the climatology. There are two kinds of rare events. One is April 3rd and 4th, where it covers a huge area. We don't have outbreaks that are that big very often. The second kind of a rarity is the Arkansas outbreak in January of this year, where that's at a time when they actually don't have very many tornadoes in Arkansas in the middle of January. So that even though it did cover a very big area, it was a peak. It was a big surprise. Note that there's no information on the intensity here. So the fact that April 3rd and 4th is also rare for having a huge number of violent tornadoes. I'm not even looking at that right now. We've looked at all of the rarest outbreaks. And I'll show you what this figure looks like for April 3rd and for January 21st. The rarest outbreaks from 1980 to 1994, in terms of their peak rarity, and I'll find that in just a second, was the outbreak that was associated with the landfall of Hurricane Gilbert in South Texas. You don't get very many tornadoes in the Big Bend of Texas in the middle of September. That's ignoring, there is one outbreak that had a bigger thing, and that was the tornado the reported tornado with the fatalities at Newburgh, New York in November of '89. That there's some disagreement as to whether that was a tornado or not. For aerial coverage, it's the 15th of November 1988, and I'll show you those. And these rare outbreaks occur necessarily outside of Tornado Alley in time and space. Okay, now we can go to them. I'm going to show you what these look like. We come on down. Okay. Look at April 3rd, 1974. What I've plotted is the log of the probability of that event occurring. What that means is that the orange color, the actual occurrence that occurs within the orange color is 100 times the climatological probability of that location. So that over an area that is about 8% of the United States on that day experienced 100 times their climatological probability of a tornado coming close to them, and 10% on the 50% or 50 times climatology. And the peak rarity is Eastern Kentucky, that's the southern end of West Virginia, where it was about 500 times their climatological probability, the distribution of tornadoes. In contrast, we go back and look at Little Rock, from this, the Arkansas outbreak, for January. Smaller area, but it peaked at 1,000 times the climatological probability in northeastern Arkansas. Those people who live where my father grew up in northeastern Arkansas are there. That was a big surprise if they weren't paying attention to forecasts. They don't expect tornadoes that time of year. But a very small area, only about less than half the size of the April 3rd outbreak, was, say, 50 to 100 times the climatological probability. Okay. We go back and we look at the really, really big events. Hurricane Gilbert on September 17, 1988. The peak probability here is about 1,300 times climatology, right there on somewhere around Del Rio, but a fairly small area that had much control at all. And then finally, the big outbreak, or the biggest aerial coverage on 15th November 1988. And remember, at this time of year, the peak threat for tornadoes is right there. And we had tornadoes from the Texas Panhandle up into southeastern Minnesota on that day. This covers the area 50 times this is actually the second highest peak probability. It's like 1,200 times climatology. And the area where the probability is 50 times climatology is, I think, 15% of the United States was 50 times the climatological probability of a tornado. So this is an incredibly rare event. And we can show you an idea of what a big event looks like in Tornado Alley at the peak time, April 26, 1991. My personal favorite tornado outbreak of all time. This is as good as it gets. These peak probabilities are at no location does it get more than 100 times climatology, or as much as 100 times climatology. And then actually, it's the area that was about at 50 times or greater was only about 2% of the U.S. It's hard to be really surprised in late April when there's a tornado outbreak in northern Oklahoma. I mean, that's just what those things happen. They're still rare events, but they aren't really, really, really rare. A tornado outbreak in northern Oklahoma in early October or the middle of November, that's a rare event. And people get caught by surprise, and those are the kinds of events that cause fatalities. There aren't very many fatalities in outbreaks in Tornado Alley for a huge number of reasons, one of which has to do with the fact that people can know what the threats are. Okay. I'm going to close with a couple of thoughts. There was a tornado forum that FEMA put together last August, and one of the things that committee came out with they wanted was they would come up with site-specific hazard estimates. What's your threat any day of the year, any place in the U.S. of having a severe weather event? This is useful to a large audience. And I think we're finally moving a little closer to those kinds of estimates. Over the summer and early fall, we're planning on producing a climatology of significant tornadoes and with some luck, a climatology of violent tornadoes using the Grzulis data set of 75 years. And we've got some ideas how to deal with the report changes over time, but it's very hard. One of the big things that makes it hard is that changes in reports aren't the same all over the country. If you look at the total number of tornadoes per year in Oklahoma from 1954 till now, it's almost a stationary time series. That value hasn't changed very much. If you look at that number in northeastern Colorado, you go from none for the decade of the 1960s to apparently now it's probably the peak location for having tornadoes anywhere in the U.S. Those kinds of things, and the different hazards also have similar problems. So that any effort to try to deal with the report changes has to be done extremely carefully. We've got some ideas, but they're going to be hard to come up with. But I think we're finally learning, we're getting a little closer to finding out what's really out there. And that's all I say. Thank you. Not too bad.
Any questions?
Les.
I just wanted to mention, this goes way back early in your talk. It's hard to remember that far back.
I agree.
But one of the things I wanted to mention is I happened to be in a meeting, I think it was late 70s, early 80s, in which I heard an MIC in the southeast U.S. say in this meeting that if they got a report of tree limbs down, that would verify a warning that they had issued. If they had a report of tree limbs down and did not have a warning issued, that did not constitute a report. And they would also, of course, if they had a warning out, beat the bushes in that area.
Or beat the trees.
Yes, and if they did not have a warning out, they would not seek reports.
Yeah, there are dangers. And I have the most confidence in the significant tornado work. In the tornado, and wind and hail I can't separate out, which I have the least confidence in. One of the things we've done by focusing on yes or no when an event occurs on a day, we've made the statistic a little more robust so that we aren't going to worry about the fact that they might find 20 reports, and we also aren't going to worry about the fact that they the exact timing of the report. So some of the issues that Greg has to deal with in doing algorithm development, where if the report's off by an hour, that does him no good. For me, an hour is that's the same time. Yeah.
You touched on it briefly in your talk, and I was hoping you could go more into it. It's okay. When you talked about comparing years of similar numbers, and it seems like the next step would be to capture synoptic trends.
Yeah.
Is that like the next step?
Yeah, there's some. Yeah, we've got a. Actually, I don't know how this happened, but a guy from the insurance industry, with lots of computer time, does he lots of number crunching, and we'll let anybody number crunch for us. One of the problems comes down to that the reanalysis, which would be in one way a nice data set to use, goes back to January 1, 1958, which is an incredibly unfortunate date for the reanalysis to go back to. If we went back one more year, we would have the best year ever. In the, what was that? It was April 1, 1957, when they, or June 1, 1957, when they changed from 3, 9, 15, and 21Z soundings to 12 and 0. And the reanalysis project will never go back to the previous period. So if we want to do the really big years, 53 and 57, we have to actually process all of the soundings. And this just dramatically increases the workload. And students here now can do that. But that's a non-trivial exercise.
Earlier, also when we were discussing peak years for times of the year, tornadoes was April, certainly. I was wondering if they'll partly be reported tornadoes, but the type of, it's April and it's tornado season, just finding.
So there's some of that perhaps in the any tornado reports. The significant tornado reports appear to be much lower levels. That data set appears to be, its statistical properties are nice. And so I got pretty good confidence in that. One of the nice things about the Grzoulis data set is that one guy spent 20 years going through all of this. And so he made decisions that are hopefully reasonably consistent. And beat the bushes for small, town newspaper stuff. It's a really remarkable data set. And I think that, it's not perfect, but at least gives us a pretty good picture of what's going on what's happening. But the any tornado database, I think, is that going on. Hey, Rick?
Yeah, you pointed out that the rate of killing tornadoes is going downhill or less each year. But do you think maybe that has something to do with also better building practices in the last 20 to 30 years also, that people are being protected better in their residences? And things
Absolutely. It's also easier to warn people in a metropolitan area. Trying to warn everyone when all you have are people living on farms, that's pretty hard to do. And it's not clear that it's because of what we're doing with the death toll. The death toll is going down, because we can look at another variable. This is lightning deaths per million people over, and it also goes down. It goes down slightly differently, and the way people die in lightning, in terms of it's almost always individually, rather than 30 or 40 at a time as in a tornado, makes it a little different. We don't do a whole lot to protect people against lightning in our forecasting. So I don't know exactly what's going on. I think the real answer is that it's a combination of societal effects and also our improvement in our watches and warnings and dissemination of that kind of product. It's a little bit like the Red Queen in Through the Looking Glass, that we have to, if we're going to continue to have the death toll drop, we're going to have to run as fast as we can to stay in the same place. And that's not necessarily going to be very easy. But it also means there's not a whole lot we can do to limit the death toll in tornadoes. We're down to about 40 per year on average. Not very many people. Yeah, Jim.
Harold, while you got that slide up,
yeah,
I just want to offer you an observation on that. If you take the centroid of that slide around 1940, previous to that time, the major method of transportation for most people who were outside getting someplace would have been horse and buggy, the vast majority of the population.
Yeah.
After 1940, most people were in cars traveling.
Yeah.
Now, a lightning strike to a horse and buggy, I rest my case.
No, you're right. You're exactly right. That may be a big part of it. That's one of the reasons why, I mean, I can think of lots of reasons for the lightning to decline. I can think of lots of reasons for the tornado death rate to decline, but those reasons aren't the same reasons.
Right.
So the fact that they both go down about the same way, and the fact with the lightning, you can even see, the dashed line is the rural population. You can actually see a hint of it leveling off in the 30s, in the Depression, when people stopped moving from the country to big cities. And then we accelerate, and we can actually see this trend of rural population in fatalities in Spain and France as well. So, I mean, it's...
I just think demographics has an awful lot to do with it.
Certainly, I know it's absolutely true for the lightning, and it's probably true for the tornadoes, but you know, the fact that we've eliminated the really huge tornado death tolls, while we've been putting people into big cities where conceivably we kill a bunch of them at one time.
Harold, you might take a look at the country's dependence on agriculture and number of single-family farms, etc. during that
Well, we can see that goes along with it, but it's one of those things that it's, I mean, I know that the trend goes like that. The only question is, you know, is that a cause-effect or just, or if there's a cause-effect relationship with any of those?
You have to be outside.
Yeah, well, for lightning. But, you know, that's what I'm saying. I can understand the lightning trend. I don't understand the tornado trend if I just use the same lightning information. I mean, you don't have to be outside to get killed in a tornado. It may be harder to kill.
Well, what about better communication?
That's part. All those things go in. That's what I'm saying. I don't know. The fact that the two trends look alike, I think they may look alike just for coincidence and not for the same reasons. Get you?
Yeah, you mentioned that earlier that the 20s were probably the most fatal decade for tornadoes. Even discounting the price-big tornadoes. Have you ever done anything by taking, say, the 20s death tolls and the tornadoes from that kill all the people then and overlaying them onto like a 1990 metropolitan geographic trend and try to see what the damage was on that?
I know somebody who can do that for me, but I haven't done that. Roger Pilkey Jr. probably is someone who I can probably talk to actually doing that project.
How bad would it?
Yeah, I mean, one naive estimate says everything we've done saved 1,700 lives last year. I mean, if we take that trend on out from the 1880 to 1925 on to now, the average, I think we figured at one point there have been 14,000 lives saved by the change in the death rate.
Okay, we're going to end the session. Lunch, if you could be back at about 20 till, not
20 to 1.
Okay. 5 minutes for lunch. Power bars. We're going to try to start the forecasting workplace a little bit quicker. Lunch will be served outside here. There'll be 2 lines, so it can go twice as fast. So enjoy lunch.